Hello everyone, and welcome back. Today we're going to continue our exploration of multivariable calculus and focus on how to find maximums, minimums, and saddle points for three-dimensional surfaces. So definitely if you don't know how to do this in one dimension, definitely make sure you know how to do that because that will definitely help out with some of the conceptual and calculation things that we need for this topic. And also in case you don't know how to, for example, solve systems of linear or even nonlinear equations, that's definitely going to help out a lot too in this exploration. Let's first off do a quick overview of some of the basic principles that you definitely should already know from single variable calculus. So let's assume that we have a function that's continuous and of course differentiable on this particular interval, say from minus infinity to infinity. So from this picture you should be able to see that we do have one local maxima and one local minima located at those circled points there. And if I, for example, chop this function off at, for example, a lower bound and a upper bound, then I'm going to have, for example, a local minima there and a local maxima there, where the rest of this curve is going to be infeasible for whatever reason I have decided to truncate that domain, right? So in this particular picture, if this is x is equal to a, and this is x is equal to b, and this function in gray is, for example, f, then the domain, by definition, for this function is going to be equal to the closed interval, let's assume, AB. Let's also fill in those points so nobody think that's an open interval or something like that. Because keep in mind, if it's an open interval, those endpoints cannot be classified as local maxima or local minima, which I'm not going to go into here, but you definitely should know how to justify that. All right, so how can we determine this from the numerical standpoint if we, for example, don't have a graph? So there's obviously some properties that relate, for example, maxima and minima. For example, for a maximum value, the derivative of the curve at that particular point is going to be equal to 0, and that actually is going to be the same for both the maximum and minimum values. The only difference is the second derivative of the curve at that point is going to be negative for maximum values, because remember the curve is sort of facing downwards at maximum values and the curve is going to be facing upwards, or concave down like a frown or concave up like a cup, for minimum values, right? So the second derivative for minimums is going to be positive. Now, just because the derivative is equal to 0 does not mean that the curve is a maximum or minimum, because keep in mind it could be something else. So it could be a point, for example, like this. Basic example would be like x cubed or something like that. Notice that here at the origin we do have a horizontal tangent line, but it is neither a max nor a min. So in this case, this would be neither a max or a min, because obviously the derivative is equal to 0, but the concavity or the convexity at that point is also equal to 0 as well. Right? Now, just a quick reminder for endpoints. Notice that for closed endpoints, so for closed endpoints, could be maxima or minima, but the derivative of the endpoints does not exist. At least the classical two-sided derivatives at the endpoints will not exist, because we need, for example, left and right limits for a derivative to exist, and you know the left endpoint doesn't have a left limit, and a right endpoint doesn't have a right limit as well. Okay? And not all endpoints are critical points as well. I just wanted to mention that also, because that's also a counterexample that some people forget. So not all endpoints are critical points. And when I say critical points, I mean local max or local min. So can you pause this video maybe and think of an example where not all endpoints are critical points? Probably the easiest example would be a horizontal line. Because if you classify that as a local max, then that means that is a local max too, and any other point on that line, right? So that is definitely something you need to keep in the back of your mind. Now that we've reviewed some of the basic topics associated to Extrema in one dimension, now let us increase the dimensions a little bit and talk about what we mean by a critical point in 3 dimensions. All right, so now let's let f, for example, instead of mapping r to r, let's assume f maps r2 to r. So that is for every x, y pair you have, I'm going to give you a real number back. So definition. So a point AB is a critical point of f if the partial derivative of f with respect to x at AB is equal to 0 and the partial derivative with respect to y at AB of f is equal to 0, or one of these does not exist. Right. And you can sort of think about what's going on here with one of these does not exist, because those topics sometimes can be a little confusing, and the graphs sometimes a little bit misleading, especially if I don't computer generate them. Right. So the primary thing I'm going to be focusing on today is, for example, this scenario. Now let's actually see if we can summarize this in one statement, right? Because if the partial derivative of f with respect to x of AB is equal to 0, and the partial derivative with respect to y at AB is equal to 0, then the gradient of f at the point AB, which keep in mind is just going to be equal to f of x of AB times the unit vector in the x direction plus the partial derivative with respect to y at AB times the unit vector in the y direction, that's going to be equal to 0 times 1, 0 plus 0 times 0, 1, which is going to be equal to 0, 0, which we usually write as the gradient of f at AB is equal to 0, where 0 here is not the number, but 0 is the 0 vector. Okay, so we can more simply write that AB is a critical point if the gradient of f at AB is equal to the 0 vector, right? Which is a shorter way of defining a critical point. Now that we know how to define a critical point in higher dimensions, now we seek to classify those critical points, for example, as a minimum, a maximum, or what we're going to call a saddle point. So the first piece of machinery that we need to define here is what is called the Hessian matrix of a function. So the Hessian matrix of a function f evaluated at some point, let's say AB, where AB is in the domain of f, is going to be given by, so for 2 dimensions we're going to have a 2 by 2 matrix, so it's the second partial derivative of f with respect to x both times evaluated at AB, then the mixed partial second derivative xy evaluated at AB, and then the mixed partial yx derivative evaluated at AB, and the second partial derivative with respect to y evaluated at AB. And keep in mind this is a 2 by 2 matrix because f is mapping R2 to R, right? So this is always going to be a square matrix, but always, even if you're working in 3 by 3 or 10 by 10, this is always a matrix of all second order partial derivatives. Okay, so for example, I'm just going to go ahead and write down the 3 by 3 matrix just in case you're curious, because some people would think, oh, it has a third derivative in it since we're working in R3. So for example, if f sends R3 to R, then the Hessian matrix of f evaluated at some point, say A, B, and C, but I'm not going to write the A, B, and C part because it's just going to be A, B, C in all of the points. This is just going to be equal to fxx, fxy, fxz, let's call z the third dimension, and then fyx, fyy, and fyz, and then fzx, fzy, and fzz. Right, so that would be the 3 input dimensional Hessian matrix for a multivariable function f. Okay, and keep in mind that as long as your second partials are all continuous, then this matrix is a symmetric matrix, right? So let's actually write that down. So if all partial derivatives or second order partial derivatives, actually no, if all partial derivatives are continuous, then you remember by Clairaut's theorem, fxy is equal to fyx, fxz is equal to xzx, and so on. That means the Hessian matrix is going to be a symmetric matrix, right? Which is represented by the transpose of that matrix is equal to the original matrix. So now that we have the Hessian matrix defined, now we're going to introduce a theorem that is going to help us classify a point as either a maximum, a minimum, or what we're going to call a saddle point. So theorem. So we're going to let D represent the determinant of the Hessian matrix evaluated at the point AB, and suppose that the gradient of f at AB is equal to 0. Right? So if the gradient of f at AB is equal to 0, the 0 vector, keep in mind because the gradient is a vector, and also the Hessian of a function at a point AB is a matrix, right? Therefore, the determinant of the Hessian matrix of a function f at a point would be a number, right? So D is going to be a number, HF is going to be a matrix, gradient is going to be a vector, in particular the 0 vector. So what values of D could D be? So D again could be positive, D could be negative, or D could be 0. So let's look at all of them. All right, so then the following are true. Then 1, if D is positive and the second partial derivative with respect to x of AB is greater than 0, right? So that's one scenario. Another scenario is that D is greater than 0 and the second partial derivative with respect to x of AB is less than 0, right? So these actually relate directly to the one-dimensional calculus. So if the second derivative of a function is positive at a point, was that a max or a min? So that was our local min. So AB is a local minimum, and if the second derivative is negative, then AB is a local maximum. So these two actually reflect directly from the single variable calculus rule. Now third, this is where it changes a little bit. So if D is negative, then AB is what we refer to as a saddle point. So AB is a saddle point, right? And in case you don't remember what a saddle point is, if you remember, for example, z is equal to x squared plus y squared, that's probably the most infamous example. That's where, for example, we had a maximum, a minimum in, for example, one direction, and then we had a maximum in the other direction, in particular at the point 0, 0, right? And you can generate the surfaces in MATLAB to sort of get an idea of what a saddle point actually looks like. Now, so we have positive, negative, and the last case is going to be 0. So if D is equal to 0, it's inconclusive and you have to do more investigation on it. Now, when I say inconclusive, if D is equal to 0, it could be a max, it could be a min, it could be a saddle point, but you have to do other methods in order to investigate that, which we won't get into today. Right, so let's get into just a bit of theoretical discussion on how to calculate, for example, D, because that's used for this, what is called the second derivative test. So if we're working in the realm where R2 maps to R, keep in mind the Hessian matrix of F is going to be equal to fxx, fxy, fyx, and fyy. So that means the determinant of this Hessian matrix is going to be the determinant of that 2 by 2. So it's going to be fxx, fyy, minus fxy, and fyx. And if the partial derivatives fx and fy are continuous, that means this determinant can be represented as, for example, fxx, fyy, minus fxy squared. Right? So that's if your first order partial derivatives are continuous, we can use Clairaut's theorem to simplify that expression. And if we have, for example, a 3 by 3 matrix, for example, if F maps R3 to R, right, what is our Hessian matrix going to look like then? So the Hessian matrix is going to look like, for example, fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, and then FZZ, and we need to find the determinant of this 3 by 3. So if you took linear algebra, you should remember that finding determinants of 3 by 3 and higher matrices can be especially annoying, but if you are familiar with it, what we can do is, for example, expand across row 1 by using the expansion of cofactors and minors, which is usually the most common way to do that. So we can say that D can be represented, for example, as fxx times the determinant of, for example, fyy, fyz, fcy, fzz minus fxy times the determinant of fyx, fyz, fzx, fzz plus fxz times the determinant of fyx, fyy, fzx, and fzy, and then you can use the 2 by 2 formula to evaluate those 3 2 by 2 determinants, and then you're going to get a, I guess, subjectively long formula for the determinant of the Hessian matrix, and you could imagine what the determinant of 4 by 4 and higher would be, but generally speaking, you could find all of these determinants if you really wanted to find them, although that calculation may be a little bit tedious. Now what I want to do is go through a couple examples on how we can use these principles to first find critical points, and second, classify those critical points as either a maximum, a minimum, or a saddle point. So the first example that I want to illustrate is for the following function: fxy is equal to x squared minus y squared. So obviously we know, if we're familiar with this graph, that 0, 0 is going to be our critical point, and that critical point is going to be a saddle point. But here I want to use these principles to verify that. The next example is not going to be as trivial, but this is just sort of a warm-up for that. So the first thing that we need to do is calculate our partial derivatives first and second order. So the first partial with respect to x of xy is going to be equal to 2x. That means the second order partial with respect to x is just going to be equal to 2 for all xy. The partial derivative with respect to y of xy is going to be equal to minus 2y, and the second partial with respect to y is going to be equal to minus 2 for all points xy, and the partial derivative with respect to xy of xy, and also the partial derivative with respect to yx of xy are both going to be equal to 0. Okay, because if you take the derivative with respect to, for example, either of these functions with the other variable isn't present, so it sort of disappears. So once you have all of these second order partials, you can calculate the Hessian of the function at a particular point, right? So the Hessian of the function at any point xy is going to be equal to 2, 0, 0, minus 2, and the determinant of this Hessian function at any point xy is going to be equal to minus 4 minus 0, which is going to be equal to minus 4. So the value of D, the determinant of the Hessian, is negative 4 for all points in the curve. So once we find our critical points, then that means that critical point will be a saddle point. Right? Now we haven't found any points to classify as a saddle point, but once we do find them, since the Hessian at every point, in particular the critical points that they exist, is negative 4, that means of course that will be a saddle point. So let's find our critical points now, which we know is going to be 0, 0, but let's find them if you don't know how to find them. So in order to find critical points, we need to find the gradient of f at a point xy, which we know is going to be equal to 2x times the vector 1, 0, and then plus minus 2y times the vector 0, 1, and we need to solve this equation for 0. So this is where the systems of equations is going to come into play. So the first equation that we have is 2x is equal to 0. The second equation that we have is minus 2y is equal to 0, and we need to solve the system of equations for all points xy that make this true. This is a very simple system of linear equations. In particular, the only solution is going to be xy is equal to 0, 0. All right, so once we have our Hessian function, right, keep in mind generally it's a function of x and y, but if we evaluate this at 0, 0, even though the Hessian was just a constant, at 0, 0 in particular it also is equal to the same exact constant, negative 4. This means that what? So let's actually summarize this conclusion so we sort of get in a little routine. So since the gradient of f at 0, 0 is equal to 0, And the determinant of the Hessian matrix at 0, 0 is negative, -4, but it generally is negative, right? That means 0, 0 is a saddle point. Right, now that example is fairly straightforward, just so let's actually go through another example that is not as trivial and sort of see if we can follow the same exact process. So let's consider this function, f of xy is equal to x cubed y plus 12x squared minus 8y. First, let's find the critical points, and then we're going to classify those critical points as either a minimum, a maximum, or a saddle, or possibly inconclusive, via the second derivatives test. So again, the very first thing that we need to do, and you may want to pause this video in case you want to try this on your own, just in case you're curious if you're staying with this. But the very first thing that we need to find is our partial derivatives, both first and second order. So the first derivative with respect to x is going to be equal to what? So that's going to be 3x squared y plus 24x. Right? And keep in mind, we're going to be setting this equal to 0 eventually, so keep this in mind. So that's the first equation that we need. The second equation that we need to find all our critical points is the partial derivative with respect to y. So that's going to be equal to x cubed minus 8. So that's the second equation. And the next thing we need to find for our critical points is we need to find all points xy that satisfy the equation. The gradient of f at xy is equal to 0. So all of the points that satisfy that equation also satisfy this systems of equations. So 3x squared y plus 24x is equal to 0, and x cubed minus 8 is equal to 0. All right. So how are we going to solve this equation, or this nonlinear systems of equations? So this is actually not too bad. So the last equation only has x in it, so it's trivial to start there. So from equation 2, we should be able to see that x is equal to 2 is the only real solution that that equation has. There are two complex solutions, but we're looking only for critical points, which are in the set of real numbers, for this particular problem at least. So when x is equal to 2, we can use substitution to find the value of y that makes that true. So substituting in equation 1, we're going to have 6 times 2y plus 8 is equal to 0, which means that y is going to be equal to minus 4. And that means what? So that means the point 2 minus 4 is a critical point. It's the only critical point. So now we need to classify this critical point as either a min, a max, a saddle, or leave it up to chance of what it is if the second derivatives test is inconclusive. So the next thing that we need to do is calculate the Hessian of our function, which requires us to find the second order partial derivatives. So you should be able to find that for our example, the second derivative with respect to x is going to be 6xy plus 24, and the second derivative with respect to y is going to be equal to 0, and the second derivative with respect to xy and also yx are both going to be equal to 3x squared. Once you have your second order partials, then we can evaluate it at our critical point. So the Hessian matrix evaluated at f for our critical point 2 minus 4 is going to be equal to what? So if we plug in 2, 4 to this, what will we get? So we have 6 times 2 times minus 4 plus 24. So that's 6 times 2 is 12, and 12 times minus 4 is going to be equal to, let's see, that'll come out to minus 24. If we evaluate the second, let's actually evaluate these independently. So fxx evaluated at 2, 4 is minus 24. And then we have, let's see, fyy at 2 minus 4, that's trivially 0. And then fxy at 2 minus 4, and fyx at 2 minus 4 are both going to be equal to, what is that, 3 times 2 squared, that's going to be equal to 12. All right, so once we have those second order partials, we can calculate our Hessian at 2 minus 4. So that means the Hessian of f at 2 minus 4 is going to be equal to the matrix minus 24 and 0. And then we have 12 and 12. And then we can find the determinant of this Hessian, right? So the determinant of the Hessian of f at 2 minus 4 is going to be equal to minus 24 times 0 minus 12 times 12, which is going to be equal to minus 144, which is negative. All right, so what does that mean? So since the gradient of f at 2 minus 4 is equal to 0, and the determinant of the Hessian of f at 2 minus 4, which we just call d usually, is less than 0, that means 2 minus 4 is a saddle point. And that is how you can analyze maxima, minima, and saddle points from the perspective of gradients, systems of equations, and first and second order partial derivatives. Hope you enjoyed, and I'll see you in the next video. Take care.